What I see AI doing in the future, and I see a lot of manufacturers starting to actually work on this, is putting AI actually in instrumentation and analytics, right? So that device will then tell you, hey, something's wrong with me, constantly running diagnostics in the background so that operators don't have to go and search and see what's wrong with it, like do all this troubleshooting. The device will automatically tell you.
Hello and welcome to the Pumps and Systems podcast. I am your host, Tom Baer, a managing editor at Pumps and Systems magazine. Today, we're speaking with Brittany Baker, Global Product Manager at ABB, who's going to tell us all about real-time analyzers and their role in wastewater treatment. So, without any further ado, let's get into the episode. So, welcome to the Pumps and Systems podcast. Thank you very much for being here. Today, we're going to be talking about real-time analyzers. But before we get into that, would you mind introducing yourself? So who are you? What do you do? Tell us anything you would like our listeners and viewers to know.
Yep, absolutely. So my name is Brittany Baker. I work at ABB, which is a global manufacturer based in Switzerland. For those who do not know, I am a part of our process and automation division. So we have four different divisions. Most folks are familiar with electrification, robots, or our motion division, our drives, motors, etc. But automation is the best division in my opinion, but I may be a little biased. So I am a global product manager. My background, particularly, I've always worked in manufacturing. I have a degree in engineering. And right when I completed my undergrad degree, I went and I worked for a water analyzer manufacturer. And then I went and worked for a flow meter manufacturer. And then I came to ABB a little over 3.5 years ago. So I've always worked in manufacturing, always worked in water industry. And that's a little bit about me.
So moving into our main topic, let's start with the basics. So what are real-time analyzers? What do they do? How do they integrate with pumps? What's their role in wastewater treatment? Like, give us the real-time analyzers 101.
Yeah, absolutely. So real-time analyzers is sort of a blanket term, right? So there's different types of analyzers, different types of technologies that you can use to monitor a particular water quality parameter, right? So one that I think most folks are probably most familiar with is pH, right? Because pH is very important and it's probably the most widely used sensor on the market. There are other different ones that are more advanced. But pH is probably the most common one that we see used integrated with pumps and different systems. Different technologies, right? So you can have submersible sensors, you can have bypass sensors, which means you have to physically bring a water sample to the analyzer. There's also different technologies and principles of operations, right? So submersible sensors can use electrodes. They can also use optical light. They can also be colorimetric, right? So a lot of folks are also familiar with that. If anybody has a pool, they probably have used a litmus test where you dip a pH strip in your water, or you see what you need to add for chemicals if you have to shock your pool, right? Same idea, right? But these are devices that are going to continuously measure. So they can be as quick as milliseconds, depending on your process, or they can be batch or timed for every 10 to 20 minutes. And this is important because if you're doing real-time analysis and you're doing process control, you want pretty quick results to adjust your process as needed. So one of the more common applications that we see for pumps is chlorine dosing, right? So it's always important to disinfect your drinking water. You need to have a certain limit depending on where you are. So we will use chlorine analyzers and pH analyzers to make sure that both of those residuals are in line with local regulations. In addition to that, there's more advanced parameters that are becoming more popular. So organics is one of them. Certain primary pollutants like nitrates, phosphates, things like that. So it all depends on what you're trying to do, but that's just kind of a very general overview. So they can be a lot of different form factors, provide a lot of different information at different frequencies, depending on what you're trying to do.
So let's talk a little about aeration energy costs. So
Yes.
how do real-time analyzers help with reducing those costs, and what can you tell us about that process?
Yeah, absolutely. So I think it's first important to understand what is aeration. So aeration is primarily in wastewater applications, municipal wastewater. And what we do is we add air, very fine micro bubbles, to the water, to our wastewater, to help digest pollutants, right? So we want to get rid of all the nasty stuff that's in the water. So we inject it with air, and microbiomes will actually use that air as energy to consume all of nitrates or other things that are in the water, right? So other organics. Now, aeration basins can be very expensive to run. If you can imagine, if you had a swimming pool, again, going back to my pool analogy, and you were constantly pumping air into that pool to make sure the water was staying healthy. Okay, that's a very expensive endeavor. So, what we have done is we use dissolved oxygen sensors, right? And those dissolved oxygen sensors will look at the oxygen concentration in the aeration basin based on this process or stages that it is in that process. Okay, so we inject the air, we look at dissolved oxygen, and we adjust the blowers based on our dissolved oxygen content and where we are in the stage processes, right? So there's different processes, different biomes like to use oxygen, right? They're aerobic, or we can go into anaerobic or anoxic zones where there is no oxygen present, right? They all serve a very unique and very different purpose for getting rid of your pollutants. And just so you know, aeration basins can account for anywhere from 60 to 70% of the energy cost of the entire wastewater plant. So if you can reduce those costs by even 5, 10, 15% just by using automation, using sensors, you can save yourself quite a bit of money. The ROI is realized relatively quickly. It all depends though on the size of the plant and the integration and obviously the startup costs and the construction costs.
So, do you have any examples that you can share with us of analyzers helping wastewater plants in the real world?
Yes, yes, I do. The one that always comes up, obviously aeration basins using dissolved oxygen sensors, probably the most straightforward application. However, in more advanced processes, so we call them BNR, which is biological nutrient removal, where we're using the actual biology of the water to remove nutrients, right? So common nutrients that we see that are regulated are going to be your nitrates or nitrogen, phosphorus, and ammonia, right? So these are all primary pollutants defined by the EPA, and they have regulatory limits. Every state's a little bit different. Some may have more stringent regulations, some may not. And you're probably wondering, why do I care about phosphorus, ammonia, nitrate? What does all of this mean? So what can happen though is that when they are discharged into a receiving water stream, right? So your river, ocean, lakes, wells, when they get discharged in there and they are above the requirements, which are very, very low, we're talking like less than 1 ppm in some instances. If they exceed that limit, you can actually create toxic events in that water source. So if you think of algae blooms, right, what happens is all those pollutants will consume the oxygen that's in the water because water is a living thing. And when all of that oxygen starts to get consumed, you get hypoxic events and you see algae blooms and you see fish dies and you know all of these kind of bad things that you do not want happening. So it's important that we mitigate it as much as possible in the plant. So some examples, right? Dissolved oxygen in the BNR process, we're going to use more advanced parameters such as nitrates to see where we are at nitrification and denitrification. Additionally, at the end of the plant too, right at your effluent, right? That's a very important spot to monitor depending on what you are doing in the treatment process. So sometimes we'll do chlorination to disinfect the water one last time, but we can't dump chlorinated water into our lake. So we have to do what we call dechlor. So we'll monitor the chlorine going in and we'll monitor the chlorine going out, making sure that there is none. pH is also very important going out, right? So if you have a fish tank at home, you know that pH is one of those most important things to monitor quite regularly because slight pH changes can harm or kill fish. So it's important that that's always regulated and commonly monitored. In addition, we can look at nitrates, phosphates, or anything like that. So these are just examples, again, staying within regulation, making sure you're treating your water as well as you can. And also, if there is an event, right, which has happened, you have the ability to catch it and either A, divert it, or B, treat it relatively quickly if you have that information at your hand.
Next, let's talk about UV Vis. So, UV Vis, optical analyzer technology. What is it? How does it compare with other kinds of analyzers?
Yeah.
Give us the facts here.
Yes, yes, awesome. I would love to. So I think it's important to understand what UV vis even stands for, right? So UV is ultraviolet. It's talking about the light source, and vis stands for visible, visible light. So similar to how human beings can get X-rays and we can see our bones and we can see the inside of us, water can also have a similar experience when we put UV light and visible light through it. We can actually see the makeup of the water, whether it's inorganic or organic compounds. And this light has a very specific band, similar to how X-rays have a very specific band. UV light is anywhere from, and it's debatable. I know I'm probably sure a lot of fact checkers say, "Hey, hold on," but it's from anywhere from 190 nanometers all the way down to about 300 nanometers, and then the visible light goes from about 300 all the way down to about 720 nanometers. And I say the range changes because in different publications they like to cut it in different areas. But that's the general gist of it. And what makes the difference between the two, why we split them up, is because I like to say ultraviolet light is the stuff we can't see in water, right? I can't see nitrate in water. I can't see biological oxygen demand in water. But in the visible spectrum, that's what we can see, right? I can see color in water. I can see solids in water and turbidness or anything like that. So that's what the visible light picks up anything that we can see. The UV ultraviolet light picks up things that we cannot see, all of your organics and probably some of your more complex organic or inorganic compounds. So what's cool about this technology is that you can use different light sources, right? Common ones are LEDs, white light, xenon flash lamps, deuterium lamps, the list goes on and on and on. But LEDs and white light sources are probably the most common that we use in the industry, and we can pick what wavelengths we want to measure based on the compound that we want to see. So nitrate is a very common one that we see a lot in drinking water and in wastewater applications. In addition, we'll see a lot of UV. So UV 254 for UV disinfection is very, very common. That's probably the most popular one. But in addition, the more that you look at, the more wavelengths that you look at, the more complex compounds that you can look at. So one of those complex compounds is BTEX, or benzene, toluene, xylene. So this is commonly found in a lot of diesel fuels or a lot of oils or lubricants. It is a carcinogen, depending, benzene is a known carcinogen. Why are we looking at this? So it's common for source water monitoring. And even in some oil and gas refineries at their effluent, or making sure there's no leaks in their process or nothing's going on. So they said it's a wide range. And what really makes me excited about this technology is that it's ever evolving, right? There's so many compounds out there, and it's just a matter of, okay, do we have the light source? Do we know the wavelengths that this absorbs at? And can it be measured in a ppm or ppb range, right? So parts per million or parts per billion. So it's a pretty cool technology. I don't know if I answered your question completely, but or indirectly, but that's a little bit of the gist of how it works. And so another thing is the form factor it comes in, right? So it can be a submersible probe, which for all intents and purposes just looks like a pipe, um, or it can be in a bypass cabinet, like again, where you plug a sample, bring a sample up to it, and it goes through the light source and it comes out. So
All right. Yeah, no, that answered my question. And it's interesting to learn about that kind of technology because I don't know much about it. So,
yes, yeah, it's been around for a very long time. So the first basis of this technology was actually colorimetric analysis.
Mhm.
So colorimetric analysis is just like in the word, right? You are actually changing the color of the water. The most common one is the DPD method, which is used for chlorine. Do not ask me how to pronounce the DPD method. It's a mouthful. It's probably like a 20 character word. But it's used for chlorine, so free chlorine or total chlorine, and it turns the water this pinky purpley color. And depending on the intensity of that color, so the darker that color is, the more of that residual or more chlorine you have in the water. The lighter that color, the less you have of that water. The only hang up, so colorimetric analyzers are excellent, right? I love them. They have known applications. They're proven. They're very accurate, very reliable, very repeatable. The one or two downsides to a colorimetric analyzer is that you have to pump a sample up to it, and it has to be a treated sample. When I say treated with air quotes, I mean it has to be under a certain temperature, pressure. There can't be a lot of particulate matter in there, so no turbidity or solids or anything like that that can clog the line. In addition to that, you're adding a chemical to the water, right? So anytime you add a chemical to water, it has to be discharged to a sanitary sewer. It cannot be recharged or put back into the environment. And that's fine. However, me living in Colorado, we have a lot of issues with drought. So
Mhm.
every time you're taking a sample for your chlorine or for phosphorus or ammonia or fluoride, these are just common colorimetric parameters, right? Um, you're wasting water, right? So, what is the cost of that sample? And that's an important question to ask sometimes, depending on where you are. Sometimes it may not matter, but other times it may be a very costly measurement just based on that one little principle right there that you have to dispose of the sample. So UV vis technology does not add any kind of reagent or chemical reaction to the water. It is literally just water going through what we call an optical path length. The light shines through it, and that's it. That's all we're doing. It's like an X-ray.
Yeah, that sounds a lot better. Though, and if you're colorblind, can you like understand what the that's not an official question. That's just something that I was wondering.
Yeah. So it's funny you say that because similar like if you ever seen like a litmus test, like those little color strips where you dip them in and you have a color wheel,
Mm.
they will actually, like, I've been in water treatment plants where they're like, okay, are you colorblind? And it's like, if you are, you can't do any of those tests because you can't see the difference between the colors. So yes, it is a thing. It's a known thing. And it is silly, but it's the reality that some folks have to live with, right? That they are
Hmm.
colorblind, they can't see this. So what am I supposed to do?
Okay, so let's move on to regulatory trends. So, how do you see those influencing the use of real-time monitoring when it comes to things like stricter nutrient limits, real-time compliance, things like that?
So these are actually quite they're benchmark for a lot of manufacturers, right? So regulations are very important for our industry, specifically because they tell us what requirements we need to meet. They also are written around best available technology, right? So that's an interesting one. Because if the technology does not exist, well, it's hard to monitor for it, right? So PFAS, PFOS, right? Everybody's talking about this. It's the new buzzword. The problem is that to get a real-time analyzer to measure PFAS or PFOS down to the part per trillion, yes, PPT, is very, very difficult, if not near impossible. Folks are trying to do it. There are definitely companies out there that are doing it and pursuing it, and the results TBD. It's exciting. I'm excited to see what it does. But that's one thing that's important, right? What is available? Now, as far as pollutants go, known pollutants that have been defined by the EPA and NEPDES, which is the National Pollutant Discharge Elimination System, this came out with the Clean Water Act in 1972 or 74. It was in the 70s that it came out. They defined common water quality parameters that are known pollutants, right? So pH is being one of them you have to control, removing TSS or total suspended solids, making sure that all your nitrogen is removed, phosphorus, ammonia, and they keep adding to this list, but they also keep changing the limits. And this is what's very important, right? So when you go from 0 to 10, you have a pretty wide range to work with. But imagine if that 0 to 10 became 0 to 2 over a year, right? So that's what we're seeing what's happening, especially with coastal cities or areas that are in wetlands or drought restricted areas. These regulations are becoming more and more restrictive because they need to protect the existing ecosystem, or they are recharging that water and they are putting it back into the potable water system, or it's going back to the drinking water plant. So it's very important to monitor these things. So regulations are very important. And also, again, they tell us as manufacturers, where is the industry going? What are the trends? It's telling us where and how should we create these products, right? How do we market them? Are these measuring ranges? Is it 0 to 10 or is it 0 to 2, right? So that's a huge difference. And we need to meet those requirements so we can be the best available technology. So regulations are very important. They are definitely getting more, like I said, more and more strict from what I've seen in coastal areas and especially drought areas.
So, when it comes to more holistic optimization, how can real-time water quality analyzers help with that?
Yeah, definitely. So, water quality analyzers can be used in a multitude of ways, and you can use multiple water quality analyzers, right? So, for the case and example of effluent at your wastewater treatment plant, right, you have to monitor all these different things: pH, probably, pH definitely, turbidity or TSS, suspended solids, maybe chlorination, maybe UV, probably phosphorus or nitrate and ammonia, right? So I've already listed 7 things that you may have to monitor already. So manufacturers will actually create package systems where you can measure all of those things at the same time and get all of that data sent back to your control room, your SCADA system, or your PLC, and do automation control right from that one panel, right? So that's one way that's creating an easy, well rounded approach for that very specific application. There's also the instance of product loss, right? So in food and bev industries specifically, where they have a lot of cleaning place, or SIPs is what they call them. They also have a lot of deliveries, product coming in and out, product moving, a lot of piping changing. You can see product loss. So good product going down the drain, which in essence doesn't seem like a big deal. But when that product goes down the drain and it goes to their treatment facility, the operator of that treatment facility is going to say, hey, I wasn't expecting to get this giant slug of who knows what. It could be apple cider, it could be baby formula, it could be anything. And the problem with that is usually it has a lot of sugar or a lot of organics, and their treatment plant probably can't handle all of that at once. So, how does he or she know that that's a problem? Well, if they had a real time analyzer at the beginning of their treatment process, then they could see a change in pH or temperature or organic content, even color of the water, right? So I went to a facility, I won't name names, but they made a lot of teas and juices, and it was very cool because the wastewater smelled like fruit punch, right? So I don't know how many people have that experience, but when you're at a wastewater plant and the primary effluent coming out smells like fruit punch, it's not a bad day at work. But it was interesting because you could see when they were changing their process or changing the production line, right? So it would go from fruit punch to like a lemony sweet tea smell, and then it would be water, and then we'd get another batch of like a really fruity kind of like juicy clear liquid that you're like, okay, I don't know what this is, but it smells really good. And then it would be another batch of just regular water, potable water, probably cleaning solutions and everything. So it's very quick, rapid changing process. So it's really hard to capture data if you have one person going out there and taking samples. Where you have real-time analyzers, it can pick up things really, really quickly. So that's one of the many benefits. Like I said, effluent monitoring, product loss monitoring, process optimization and aeration basins, even regulatory stuff. So there's so many different ways that analyzers can help and assist you in your processes.
Yeah, and when it comes to wastewater smells, I'm sure fruit punch, lemon tea sounds way better than most. So,
Yes, it was definitely one of my favorite sites to go into a startup at and to
all right, so let's look toward the future. So, where do you see wastewater monitoring headed in the next 5 years or so, particularly in terms of AI integration, the adoption of reagent-free technologies, things like that?
I think the biggest thing, and I'm not anti AI at all, so please don't hear this as that, but the biggest gripe that I personally have with AI is that garbage in, garbage out, right? You have to give good information to AI or else you're not going to get good information out. So I think that's the first step. And what I mean by that is if you have, let's just say you have a flow meter, right? You have a flow meter coming into your plant, but you're like, this thing's a piece of junk. I don't trust it. And maybe it is a piece of junk. Maybe it's never worked. Who knows? But if that device is going to be used to feed information into AI to do adjustments on the fly, well, maybe you should get a better device, right? But the question then becomes, hey, how come you don't trust this flow meter, right? Is it something that it did? Is it not set up right? Is the area of the flow meter not correct? Little things like that, right? That you start to kind of dig around and figure out. So, what I see AI doing in the future, and I see a lot of manufacturers starting to actually work on this, is putting AI actually in instrumentation and analytics, right? So that device will then tell you, hey, something's wrong with me. I don't like, something's wrong, right? I don't feel good. There's a hiccup or something isn't right. Ready, just constantly running diagnostics in the background so that operators don't have to go and search and see what's wrong with it, like do all this troubleshooting. The device will automatically tell you, hey, you need to go and check my fuse, or hey, I need more reagents, or hey, you need to do a calibration on me. Something's wrong, right? So I think that's the first step of AI is making sure instrumentation and analytics are working the way that they are intended to work and working in the application that was designed for them. And that's the first thing. Then I think we get into the fun part of AI where it's like, oh, okay, now we can start doing a little bit more automation, hands-off control with these devices. But I think that's the first step, right? Is having that trust in our instrumentation, our trust in our analyzers, and AI will definitely help us with that. One of the other fun parts of AI too is okay, I don't know what's wrong with my device, but if I go into AI and I say, I have this device, it's doing these things, and AI spits back out at you what the troubleshooting tips could be, right? So instead of having to go through a manual and try to figure out what all these error codes are, you go to an AI device, you put in what you think is or what you're experiencing, right? And then it spits out exactly what you need to do. So I think those are going to be the really cool things for AI. And then once we get to that, I then think we'll get to the very fun and sophisticated future world of, hands free operation and automatic controlling and pumping schemes and flow schemes and all this other stuff. But I don't know if we're quite there yet because we need to have that trust in our instrumentation now. But as far as reagent free technology, so I think this is a fun one, right? Because I think there's UV Vis. I'm very passionate about it, but I think there will always be a place for reagent technology, right? And that's simply because reagent based analyzers will provide you with that repeatability and that accuracy and also measuring down to a very, very small range, right? Usually they can get down to the ppb, sometimes ppt range. Online analyzers that are not using reagents, such as UV vis sensors, they don't have that ability yet. So maybe in the future we will get there, but right now, that is a very, very hard benchmark to reach with optical sensors. But I think in the future it will improve. One area that I am excited about, though, is the developing parameters, right? So, what can we monitor in wastewater, right? Chromium 6 is one that comes up, right? So, Chrome 6, if you've ever seen the movie Erin Brockovich, that was the big lawsuit in California that there was Chrome 6 leaking into their water. That's one that's like, oh, that is an interesting parameter, right? That kind of comes up. Monochloramine is another one, right? So, monochloramine is used in drinking water for disinfection purposes. That can be measured optically without any reagents, which is huge, right? Because again, drinking water, if you're in a drought area and you're using monochloramine, you're wasting water because you have to use a reagent. But the benefit is you get very accurate, very repeatable results. However, if you go with an optical sensor, you can get those same repeatability, same results, but you're not wasting water or spending water using chemical reagents to create that reaction to get your results. So I think that there's so much to be developed and so much more to be discovered in UV vis technology. I'm very excited to see where it goes. And it's always developing, right? It's always growing, always evolving, right? And so is colorimetric analyzers, right? Their manufacturers are getting very creative with how they limit the use of water, right? So instead of using like a 10 mil sample, they may use a 5 mil sample. Just different little things that are really just like, oh, it's like, that's a genius idea, right? I wish I thought of that. That's a really clever idea. So it's definitely emerging, but the one thing, like I said, parameters, right? What can we measure? What else can we measure, right? We can do the stuff COD, BOD, nitrates. Yeah, that's fine, but like Chrome 6, that's cool. Monochloramine, that's cool. Right? What else can we do, right? PFAS, PFOs, not yet, but somebody will. Someone will figure it out. It's not going to be me. I'm not that smart.
So, before we wrap up, is there anything else you'd like to share or any final thoughts you'd like to leave us with?
No, I just thank you very much, Tom, for having me on the show. I really appreciate it, and yeah, I look forward to seeing what the future holds, and and seeing, how things change and how things evolve. And yeah, I think that really wraps it up nicely. So thank you again for having me, and I look forward to chatting in the future.
Yeah, thank you so much for coming on. It's been great getting to learn a bit about some things I didn't know about before, and I'm sure everyone's really going to enjoy this episode. Huge thanks to Brittany for taking the time to speak with us today about real-time analyzers and wastewater treatment. If you're listening to the podcast and would like the chance to watch it, head over to our YouTube channel to see the full video version. That's going to do it for this episode. Thank you so much for listening or watching, and we will see you next time.